Assalamualaikum, salam sejahtera and very good day. Before I start my presentation, I would like to thank to the organizer for giving me the opportunity to share some information about Malaysia's hydroclimate due to climate change. The topic of my presentation today will be projected changes in Malaysia's hydroclimate. Climate change is undeniable the greatest challenge of the 21st century. Over time, the effects of global warming will increase the global temperatures, changing precipitation and sea level rise. Because of these changes, it is expected to worsen the frequency, intensity, and impacts of some types of extreme weather events, which is more extreme events are expected to occur around the world, such as more intense rainstorms, longer droughts, extreme flooding, more intense cyclones, more intense storms, higher peak wind speed, and higher storm surge. All these disasters impose heavy costs on society and the economy. Poor developing countries, which most vulnerable to the impact of climate change, are among the most affected when people living there often depend heavily on their natural environment and they have the least resources to cope with the changing climate. As we all know, water is very important resource for life and economic development. However, climate change is likely causing parts of the water cycle to speed up as warming global temperatures increase the rate of evaporation worldwide. More evaporation is causing more precipitation on average. We are already seeing impacts of higher evaporation and precipitation rates, and the impacts are expected to increase over the century as climate warms. Higher evaporation and precipitation rates are not evenly distributed around the world. Some areas may experience heavier than normal precipitation, and other areas may become prone to droughts. Some climate models predict that coastal regions will become wetter and the middle of continents will become drier. Also, some models forecast more evaporation and rainfall over oceans, but not necessarily over land. Well, you might see that non-climatic forcing alone, such as increase in population, land development already created some pressure to the environment. Then, coupled with the factor of climate change, the negative impacts are expected to be more intense. Weather's been hotter than usual. I think you might have noticed an increase of frequency of flash floods as well as monsoon floods in our country. Other impacts include increase of erosion and siltation in the river system, increased frequency of droughts, pollution, and inadequate environmental flow. Days with extreme rainfall events have been on the rise since 1980s. Extreme wind events and number of annual thunderstorm days have also been increasingly. If you still remember in the year 2014, the big flood event caused by the seasonal monsoon has been described as the worst floods in decades. 7 years before that, another major flooding was recorded in December 2006 and January 2007. So, in the past 2 decades, there are 13 major floods have been recorded with about Rm 2.9 billion economic losses and Rm 800 million for the reconstruction of damaged infrastructures. Another impact of climate change is too little water due to less precipitation in some areas. The two last periods that the country received less rainfall were the year 2015-2016 and 1997-1998, leading to drought conditions associated with the ENSO effect or El Nino event, which affected some parts of Malaysia. This drought phenomenon caused the drying up of some reservoirs in the country and consequently resulting in water rationing in some areas affected. In Peninsular Malaysia, the surface temperature may increase by 1.29 to 1.37 degrees Celsius during the period of 2050 because of climate change. This temperature may further increase to 1.85 to 1.93 degrees Celsius during the period of 2050. Similarly, the annual temperature for Sabah and Sarawak will be increased as well. Sarawak will experience hotter weather with increasing of its annual surface temperature about 1.35 to 1.43 degrees Celsius in the period of 2050, followed by another 1.94 to 2.05 degrees Celsius for the period of 2100. The uptrend also projected for the annual rainfall, with Sabah will get highest additional annual rainfall about 813 millimeter in the year 2100, which is equivalent to 25% compared to its historical value. Similarly, annual evapotranspiration is expected to increase during the same period. As I mentioned earlier, the surface temperature may increase in the country. From our study at 11 selected river basins, which covers Muda River Basin, Perak River Basin, Selangor River Basin, Klang River Basin, Lingi River Basin, Muar River Basin, Batu Pahat River Basin, Kelantan River Basin, Dungun River Basin, Pahang River Basin, and Johor River Basin, we found that the changes in Peninsular Malaysia is about 1.34 degrees Celsius in 2050 and 1.89 degrees Celsius in the year 2100. Compared to the historical temperature of 24.33 degrees Celsius. So among these 11 river basins, Johor River Basin will get highest changes of about 1.93 degrees Celsius. On the other hand, the smallest changes will be occurred at Selangor and Klang River Basin with the magnitude of 1.87 degrees Celsius, while Sabah and Sarawak will get a little bit more changes with another 1.38 degrees Celsius in 2050 and another 1.99 degrees Celsius in the year 2100 compared to the historical record of 23.44 degrees Celsius. To analyze the average annual precipitation because of climate change, we have chosen the same river basin, then divided the period of time into 3 slices, which is the first slice is between 2010 to 2040, next slice is between 2040 to 2070, and the third slice is 2070 to 2100. So from our finding, the magnitude of changes in Peninsular Malaysia is 336 to 383 millimeter in the period of 2010 to 2040, followed by 108 to 590 millimeter for the period of 2040 to 2070, and another 167 to 637 millimeter in the period of 2070 to 2100. Sabah and Sarawak are also expected to get an extra precipitation in terms of 30-year average annual precipitation. The magnitude of changes are 105 to 826 millimeter in the period of 2010 to 2040, followed by 166 to 1219 millimeter in the period of 2010 to 2040, and another 252 to 1534 millimeter in the period of 2070 to 2100. The flood extent is also expected to increase due to changes of the rainfall intensity and duration. We found that the total area extent in 15 selected flood-prone basins may increase from the current 3,918 km squared to 6,007 km squared in the year 2030, and further increase to 6,210 km squared in 2050. However, some basins may experience decreasing flood extent, like Pulai Basin in Johor, which will decrease in flood areal extent in both periods. Among these flood-prone basins, Batu Pahat River Basin show the highest increment of about 196% in 2030 and another 217% in 2030. This is followed by Kelantan River Basin with an increment of 153% in 2030 and 145% in 2050. As I mentioned earlier, drought or more longer dry spell may occur more frequently in the country due to climate change. The more severe ones are projected to occur during the period of 2025 to 2035 in Peninsular Malaysia, while Sabah and Sarawak will experience the more severe drought in the year 2045 to 2055. In terms of drought severity, dry spells with written period of more than 30 years, which is up to 48.4% of rainfall reduction, may occur at Dungun River Basin, Kemaman River Basin in Terengganu, while in Sabah, the similar dry spells are projected to occur at the Upper Central Sarawak region, west of Northern Sarawak, Rajang River Basin, Saribas River Basin, and Lupa River Basin. Now, I would like to briefly share a portal developed by Nahrim for providing hydroclimate projection data and information, namely Nahrim Hydroclimate Data Analysis Accelerator, or NHYDA. NHYDA is the only climate change knowledge portal in Malaysia, primarily developed for providing climate change and water-related information and technology, which is crucial for present and future water-related business activities, engineering practices, and environment. And HYDA uses approximately 10 billion projected hydroclimate data under the changing climate scenarios of IPCC SRES A1F1, A1B, A2, and B1. It has 8 hydroclimate environment modules, which amongst others are rainfall, flood, droughts, and water stress condition using Big Data Analytics or BDA technology by means of comprehensive analysis and interactive visualization tools. NHYDA assists business entities, water operators, engineers, planners, and decision makers in designing, planning, and developing water-related program and risk management. NHYDA was developed with the intent to, number one, utilizing the technology of big data to analyze downscale projected hydroclimate data over Peninsular Malaysia, to provide scientific insights and support resources and water engineering, planning, and risk management, and then to reinforce sustainable development measures and climate change actions. It covers various data projection models covering future daily and hourly data. The ability of the system is to visualize the 10 billion hydroclimate data projected for 90 years, which is from 2010 to 2099 in Peninsular Malaysia in 6 km by 6 km grid base, which is equivalent to 3,888 numbers, which capable to help stakeholders in making decisions on issues of natural disasters related to water and environment. As I mentioned earlier, there are 8 modules in NHYDA. The first module is rainfall and runoff. This module calculates the specified date of rainfall with performing an accumulative summation of runoff distribution between 1 day and 8 days for each grid of Peninsular Malaysia. The second module is drought. This module calculates total weekly or monthly and yearly rainfall based on the defined 3,888 grids of Peninsular Malaysia. Then the streamflow module able to search and compute streamflow events based on the threshold value range. The streamflow events able to show the data related to 10 days prior to the event and 10 days after the event, which is the total number of days is 21 days. This information is displayed in streamflow graph, runoff histogram, and rainfall histogram distribution. Another module is climate change factor, which provides estimation of climatic changes to precipitation and streamflow. Then the next module is water stress index, which is an index calculated based on a model to represent the level of water stress in specific area. The index is calculated based on the ratio of total water demand or consumption against water yield or water availability. Water stress index is used to estimate and indicate the ratio of water consumed that deprives other users in the same watershed of water. The major features include grid-based or district level and water surplus deficit. Water simulation module. The next module is water simulation module, which generates information for analysis and support water resources management decisions while taking climate change and water stress into account. There are 4 major features implemented, which is water yield difference, water provision, and water resources. As a conclusion of my presentation, it is important to build local capacity for climate change resilience. Climate resilience is strengthening a system to withstand climate-related shocks or stresses where adaptation and resilience intersect. Climate resilience is the capacity of a system to cope with or recover from multiple shocks while retaining the essential component of the original system. Therefore, it is greatly important to prepare a climate resilient framework which can improve our understanding of environmental processes and better equip governments and policymakers to develop sustainable solutions that combat the effects of climate change. The climate resilient frameworks is an analytical, system-based approach to building resilience to climate change. The goal of this structured framework is to build network resilience that is capable of addressing emerging, indirect, and slow onset climate impacts and hazards. The climate resilient framework has proven helpful for cities working with numerous multi-stakeholder cross-sector issues that arise when trying to address issues of climate change, uncertainty, and planning. So this is all from me today, and I would like to end my presentation now with thank you very much for your attention. Thank you.